All right, so today we're going to talk about applying sine and cosine functions to real life situations. Taking that data and graphing things by hand, and then we're going to also put it on the calculator. All right, so we're going to skip through the first 2 pages here and start right here. Okay, so we're going to take a chart of values. And the cool thing about sine and cosine graphs is that if we know the max and the min and the midline and the period, you can come up with a function and you don't have to have the calculator do a regression model for you. And so by hand, it makes things very easy. All right, so the first thing I think we should do is to, make our chart a little bit more legible. Okay? And we're going to plot this data by hand. So I'm giving you a function of t, and I give you some values of t. And so we're going to graph f of t. And the first point's going to be 0, 0. That's easy enough to graph. And then at 2, f of t is 3. So we're going to plot a point at 2, 3. And then at 4, we go down to -3. Oh, no, I'm sorry. We go to the midline. Go to the midline. And then at 6, we go down to -3. I was really excited to get to the negative value there. All right, so we're going to go to 8, back to the midline, and then at 10, back to 3. And then we're going to connect the dots. And so from this data, do you see how we could probably name a sine curve? Okay, so the first thing we need to do is figure out what the midline is. I like to figure that out first. So our midline here is
0.
Y equals 0. Good. Our amplitude is 3. It's clearly 3. I agree. So this is our amplitude. Now, we're not explicitly told what the period is, but can you figure it out by looking at the graph?
8.
It's 8 because that's the distance it takes to go through one complete cycle. You're right. So the period here is 8. And now we have to go about naming our curve. Now, our function is going to be f of t. So it's going to be a, and we'll name a sine curve first. So sine of b times t minus c plus d, where a is the amplitude, or the amplitude factor, and then b is the period factor, c is the phase shift, and d is the midline. Okay, so let's name a sine function first. Okay, so which sine function would we like to name? We have to figure out where we're going to start. Yes, ma'am.
F of t equals 3 sine of x.
3 sine of, well, t.
Oh, t.
Minus 0 plus 0, right? I'm just going to show that. Now, the thing is that we have to consider.
Is that 4?
Well, no, how do we solve for that? Where?
It's 2.
Good.
Is 2 pi over b.
The period is 2 pi over b. And what does our period equal here? 8. So we can cross multiply here and get 8b equals 2 pi. So b equals 2 pi over 8, which is pi over 4. So pi over 4 goes in here. Okay? B, I think, is the most difficult thing to find. In order to find b, you have to know what the period is and set it equal to 2 pi over b and solve for b. So that's not a difficult calculation. You just got to remember to do that. All right. Part B says, is it possible for more than one trig function to describe this data?
Yes.
Obviously, the answer is yes. There are infinitely many. We've only shown part of the curve. So let's give it a try. What else? What other name could we give it? I'm going to color it where we're going to start. Where are you starting? Tell me where you're starting.
4.
4. Okay, so he's decided he's going to start at 4 and name it. And what would that be? F of t
-3
equals -3 sine. Does the period change? The answer is no. Once you've calculated the period for a graph, it's for the entire graph, and it goes on infinitely in both directions. So the period never changes, which means the p factor never changes. So this will be pi over 4 times t
-4.
minus 4. Good, because the phase shift now is 4. He started at 4.
And then +0.
Plus 0. Now, do you technically have to show that? No. But I'm just showing you for discussion purposes that d is 0, because that's the midline. All right, let's name another one. All right, you want to name a cosine? Where do you want to start? At 2? Okay, I like it. That would be where we were starting. So there would be f of t equals, good, 3 cosine pi over 4 times t minus 2 plus 0, which you don't have to show. I'm just showing it there. On a quiz or test, I would never ask you to show the d. You wouldn't have to show that. All right. Let's just name a negative cosine just to be
Start at 6.
complete. Yep, we'll start at 6. And that would be a negative cosine, even though we don't see the entire curve. Okay, so that curve would be
-3
3 cosine of pi over 4 times t minus 6 plus 0. Yeah. Perfect. So we can take data and come up with an equation, many equations actually that will describe the same data. Okay, we call these, like I mentioned earlier, sinusoidal curves. And now we need to talk about how we put them in the calculator, because the calculator can be a little bit tricky, but it won't fool you guys, right?
Yes, right.
Okay, so we're going to put, first of all, I want you to be in, we're going to plot some data first, because I want you to plot your data. So we have to be in what mode?
Stat plot on.
Yeah, we have to turn our stat plot on. Everybody know how to do that? We go to mode.
Second.
No, I'm sorry. Second
Y.
second y equals. You're right. And you turn your stat plot on. Now, if you're in y equals, there's another way to turn your stat plot on. You can just hop up here to see when it's blinking. You press enter and it turns it on. And if it happens to be on and you want it off, you can just hop up there and click enter. It's like a toggle button, toggle switch. Okay? So I'm going to leave mine on. Now, how do we enter our data that we had from our list? Do you remember from last year how we enter data? We're going to edit our statistics, right? So we have to hit the statistics button and we hit edit and we press enter. And someone was kind enough to type in the data for me yesterday. So I'm going to let you guys put the data from our function of time into your list 1. I want you to put the t values, and in list 2, I want you to put the f of t values. So I'll give you a second to do that. Okay. You guys are all quick. Do you have it done yet? Look at that. All right, great. Now, if your stat plots are on, how do I look at this data? We can zoom in on our statistics, yes, by hitting zoom. Number 9. If you have the 84 and you don't see it, you just have to scroll down to zoom stat, okay? There it is. There's our data in graphic form. And now we're going to see if our model that we came up with matches our data. And we all know it does, right? All right, so we're going to go to y equals, and we're going to type in our first equation, which happens to be 3 sine pi over 4 t. Okay, now we're going to type in 3, and then we type in sine. What happened at this moment when I pressed the sine button? A parentheses opens and it says sine. Parentheses, and what that means is insert angle here. Right? What is our entire angle? Pi over 4 times x. Now we have to use x because we're not in parametric mode in this calculator, but yes, we have to use, when we press the x button, it's going to press an x. But so we're going to go pi over 4 times x. Now, the calculator is going to use order of operations, so you don't have to put parentheses around the pi over 4. Okay? All right, so we can say second pi divided by 4 times x. And then am I done with the angle? Is there anything else with this angle? I'm done. Okay, so I'm going to close it. Now. Yep.
Would it be minus pi? Oh wait, never mind.
Now, some people are uncomfortable with the way that looks because that looks like the 4x might be in the denominator, but is it really? No, because the calculator is going to use order of operations and go pi first, divide by 4, and then I'm going to multiply by x. Okay?
So
How would we put it in the denominator? How would we put it in the denominator is if we put parentheses around the 4x. Because then the calculator would do what? It would go, it would do the parentheses first, and then it would go pi divided by the entire 4x. Okay? Now, we know this calculator, right, can do numerator and denominator by hitting alpha F4 or alpha F1. I didn't do that, but would you like to, let's try that. So let's clear this out and say 3 sine, and I always say jokingly enter angle here. And this is alpha F1, and we can hit numerator, denominator, and go what? Second pi divided by 4 times x. And then you feel better about the way that looks? Yes, okay. If your software is not updated, I can update it for you, and it'll do that numerator over denominator thing. Okay. All right. So do we feel good about that? Are we all in radian mode?
Yes.
Okay. And now we can hit graph and see if it worked. Yay! Did it work?
Sure.
Okay, great. So now we're going to see if our other named equations are accurate and match our data as well. Okay? So we're going to go to y equals. We're not going to clear this out. We're going to go to y2 and put our second equation in, which would be negative. Negative down here, 3 sine. Insert angle here, and I'm going to go alpha F1, numerator over denominator, and I'm going to get second pi divided by 4. Whoops. Helps if I pay attention to my. Now what do I have to do? You have to put a set of parentheses here, right? Because remember, the calculator is doing this. That's what you are going to do in red when it says insert angle here. Okay, and so then we're going to go x minus. Oops, helps if I put an x in there. And I'm going to close the angle argument. Okay, now, what happens if you don't do it this way, and if you put sine of pi over 4 in parentheses, it'll graph a line, not a nice sinusoidal curve. Okay, so we have to make sure that this entire expression here is in the angle spot. Okay, so we're going to hit graph and see if we have a winner. Do we have a winner? We have a winner. All right, I gotta hurry because I'm boring you guys. Here we go. What's next? 3. Cosine. Insert angle here. Alpha F1. Numerator, denominator. Second pi divided by 4 times x minus 2. And I'm going to press enter. And I'm going to see if the graph works. Does it?
Mhm.
Yay. All right. And we'll put our fourth equation, which would be -3 cosine alpha F1 gives us the numerator of the denominator. Second pi divided by 4. Oops, I did it again. Pi divided by 4 times parentheses x minus 6, close the angle argument, and I'm going to press enter. And then I'm going to graph it, and lo and behold, it works. Yes. All right, so I'm going to take this and put it over in this document, I hope. Here it is. And I'm going to go to y equals and put this in the document. That's pretty cool, huh? All right, so the one other thing I want to show you is the regression model. So you can do these on the calculator, but we're going to do ours by hand and then see if our models fit accurately, okay? All right, so how would we do a regression model? We would use our statistics to calculate. Now we have a long list of regression models here, and I don't see what I need yet. I'm going to scroll down. That's a natural log. This is an exponential. This is a power function, logistic. So there it is. So I'm going to press enter. Now that's a new one on me. Do you guys have iterations on yours?
Yeah.
Okay, we're just going to use 3 iterations. I'm going to leave it because that's the default. All right, and then we're going to say our x values were in list 1. We all know how to get list 1. It's down here if you don't see it. The second list 1, second list 2. And then the period. Do we know it? 8. And we want to store it in register. Now I want to store it in register I haven't used yet. I use 1, 2, 3, 4. So we're going to put it in 5. So how do we do that? We go alpha F4.
I did bars function.
I know, but look at how easy this is. Alpha F4. I just hit alpha F4, and what happened?
Yeah, got it.
Who likes that? I do. For the record, everybody have your hands up. Okay, here we go. So I'm going to press number 5. Okay, and then let's see what happens when I hit calculate. Now, I'm going to put this over here maybe if I can. So what is the regression telling me on the calculator? It's telling me that y equals 3 times our sine, and they're telling me the b factor. Do you notice how the calculator, though, has the b embedded? So this c on the calculator isn't really the phase shift, is it? Because we can't see the c unless we factor out the b. So I'm going to just make a note. This is not the phase shift. Okay. And so it would be 0.78539 t, right? Because this is a function of time, plus no c and no d. So I'm just going to put t here. Now, if we go to our calculator here, go second quit, and we go second pi divided by 4, guess what that number is? The same number, right? That's nice. Okay, so will the calculator give it to us too? It's more fun though for us to do it ourselves. You might not agree with me, but anyway. All right, well, so that's great. We solved an equation, but what if I wanted to know what the value of my function was when x was, or time was something other than something that was on my table? Like when x is, or when time is 3.
Second trace x, or not, second trace value.
Right, but let's see, what if we wanted to find f of 3 using your model? Now, the model for our data is what the equation that we came up with. All right, so let's use the first, should we use the very first one we came up with, which was f of t equals 3 sine of pi over 4 times t, right? And this was all in parentheses there, okay? Now, if I want f of 3, which is the time, at the time equals 3, I'm going to put f of 3 here, and then I'm going to say 3 sine of 3 pi over 4. Now, do I need a calculator for that? I hope not, right? Do we know what the sine of 3 pi over 4 is? Well, it's positive because it's a y.
Oh.
But yes, this would be, whoops, this would be 3 times root 2 over 2, which is 3 root 2 over 2. But you're right, if we had our calculator to find it. Now, I put this equation, the very first model that we did in Y1, didn't I? We could say alpha F4, which function do I want? Y1, and I could choose parentheses 3. Have we done this before? Okay.
Oh yeah.
So we can do it this way, right? And we get an answer, and what do we get? Now, I don't know if that's the same as,
It is.
well, I'm gonna double check. This would be 3 times second square root 2 divided by 2, and press enter, and sure enough, it's the same. So that's nice. Now, you guys mentioned another way we could do it. We could go to y equals, but I'm going to have 3 graphs up here. How do I deselect them? You hop on the equals key, and you can hide this one by toggling the equals off. The only one that's going to show on the graph is the one that is highlighted on the equals, okay? Yes, sir?
Is there a way to make your lines too?
The reason mine do is that I am using a far faster processor. I'm sorry. These calculators, their processors aren't quite the same speed as my computer. So I wish the answer was yes, but it's no. Okay, so we're going to go to graph. And there's my first model going through the data. Now, you guys said something about the trace button. So we would go second, calculate, which is above the trace button, the value of my function when x is 3. And we get the same thing. Okay, but it's faster to do alpha F4, isn't it? All right. And that it does. Do you have to have it open in the right window frame? You do alpha F4. No. Okay. Now, on a quiz or a test or something, I would want you guys to show me this. You know, and then you just plug in your calculator to get the answer, right? What if wanted to know what time my data was at 1. What would I have to do? That's right, we have to put it in y equals 1. So at what time t is my function at or f of t equal 1, right? So if I were to put that in my formula, it would be f of t, which is, we're going to use the first one, 3 sine of pi over 4 times t. When does this equal 1? Okay, so if I'm going to do this on my calculator, I'm going to put this in y1, which I have already, and this in y2, and find the intersection point, yes. Okay, so let's go to y equals, and I'm not going to delete any of these. I'm just going to go to y6. I'm going to put 1. And you see how y6 is highlighted and y1? So those are the only two that they're going to graph, this whole graph. So I press graph, and there it is. There's my y equals 1 going through my lovely little function. Now, gosh, that happens quite a few times. Yes.
Wait, how did you highlight?
Okay, so when I go back to y equals, if I only want the first equation to show and the y6 to show, you just hop over to the equals, and enter is the toggle switch. So if I hop off, see, that's not going to graph anymore because it's not highlighted. Okay? All right, and then I went to graph, and there it is. There's my first function, and there's that. Now, why would it happen more than once? Because we have a sine curve, and it's repeating. Okay, so let's, yes, ma'am? I'm going to go second, calculate the intersection, which is number 5, and we're going to hop over to I always, when I'm finding intersection points, like to be on the left side of it, because it's going to ask me, you want me to guess? Yes, I do. Okay, so there's my first solution. And then I'm going to do it again. Second, calculate the intersection point, which is number 5. Oops. Enter, second curve, yes. There's my second solution. Oops. And then second, calculate my intersection point here. All right, so where's the third intersection point? It's at 8.4. Is that outside of the period? The answer is yeah. So I only have 2 solutions in my period from 0 to 8. Okay, so I can't really read them, so I'm going to make this bigger. Maybe I'll make it bigger. There it is. Yeah, now I can read it. So what were our 2 solutions? We would, x1 is 0.4. I'm sorry.
0.327.
And this is an approximate answer. And then x2 is approximately 3.5674. Is that a 0? That's, yeah, okay. Okay, so that's when it's at time equals, or that's when it's 1. The function's equal to 1. Now, let's think about the equation here. We said that was when sine of pi over 4 t equals 1. Is there another way I could solve this by hand? What?
Inverse sine of 1.
No.
Divided by t.
What don't you like? We know when sine is 1, don't we? Yes. So, is this a 3? This is a 3, I'm sorry, right? That's the equation is 3. So this is, whoops. I'm getting a little ahead of myself here. This is sine of pi over 4, t equals 1/3, right? So we're going to let u equal pi over 4. Oh gosh, equations, right? Right? And then this would be sine of u equals 1/3. What quadrants is this sign positive? 1 and 2. We're going to say it backwards today. 2 and 1. Okay. So alpha equals inverse sine of 1/3. So you're going to have to help me with that. I don't know what that is right off the top of my head. Okay. So what might my first solution be? I'm going to, actually, this is t, isn't it? This is t. Is it? Oh, it's u1. Yeah, I'm sorry. Okay, plus 2 pi n. Good. Get my notation right this morning. That would be good. The u2 is going to be
2 pi minus, which is 5 pi, or 5.9.
plus 2 pi n and an element of the integer set. Now,
It's just
Oh,
pi.
it's pi, right? Sorry about that.
It's not
2.8.
yeah. I went right down that road with you. I'm sorry.
2.8.
What is it?
2.80.
Thank you. All right. So, but we let u equal what? Pi over 4t equals 0.34 plus 2 pi n and an element of the integer set. So t is going to be, I'm going to take this whole thing and multiply it by 4 over pi. And what do we get? We get t equal, or it's approximately, this is approximately. I don't know what 4 times 0.34 over pi is. What is it? 1.36 plus, well, the pi's cancel.
Yeah, it's
Did you not do it over pi?
it's 0.43.
0.43.
3.
Okay, we're just going to use that because that looks familiar to me. Does that look familiar to you?
Yes.
And I should make these t's, right? Does that look familiar to you? Yes? Wow. Okay, plus,
And
what is it?
8.
Where have I seen 8 before? It's a period. Is this all tied together? You're like, I don't want it to tie together this much. Pi over 4t is approximately now 2.80 plus 2 pi n and an element of the integer set. And then I'm going to multiply everything by 4 over pi and get t equals approximately, now you go 4 times 2.80 over pi. What?
3.57.
Plus 8n. Oops, my element thing is going a little haywire. Here we go. So gosh, that we we can solve this equation by without the picture, and we can solve it with the picture. So graphically and numerically, yes? If I asked you to do both, could you do it? Begrudgingly maybe, but could you do it? And do those numbers look familiar? They do, don't they? All this from a bunch of data that we started out with. And you were like, that data looks so easy, and look what it turned into. Anyway, all right, so let's do another problem. Number 4. We're going to talk about some physics. Lovely, I know. Okay, so what we're going to do is talk about a weight is going to be suspended from the ceiling, because you know we all in real life suspend weights from ceilings,
Yeah.
by a spring. Okay, so here we go. I'm going to draw a picture. I'm drawing, this is my ceiling, and I'm suspending a weight. There it is, from a spring. There it is. This is what you do for relaxation, right? Is you hang things from the ceiling and then you disturb it. And then just watch it. All right. So if the weight is disturbed, it will bob up and down. Everybody agree with that? Makes sense to me? If D is the distance in centimeters from the ceiling to the weight, so D is going to be the distance from the ceiling to the weight. Okay, so D is the distance, and when it's motionless. So let's talk about when it's motionless. When it's not moving, it's in a state of equilibrium. Now, what do I mean by that? That's in its natural state, where it would be if everybody left it alone. Right? So, if it's in its state of equilibrium, this is its state of equilibrium. When I disturb it, what does it do? It moves from equilibrium. So equilibrium almost feels like something in our sign language. The midline, yes, equilibrium is the midline. Does that make sense to everybody? Did I spell that right? Mm-hmm. Are you sure? Or it's wrong? No, it's okay. Okay. So I have a graph here that I put on my calculator and then imported it into this. So it says describe the midline, the period, the amplitude, and the min-max values of the graph. Okay, so if it's motionless and it's in equilibrium, that is the midline. So this is saying it is 10 centimeters from the ceiling. So our midline is 10. Okay, so on my graph here that I have of showing the motion, I'm going to put the midline here at 10 because I know it's 10. I gave you the scaling because I showed you the window that we're viewing it at right now. The X scale is in scaling of increments of 1, and the Y scale is 2. And the Y is starting at 0. So this means this is 2, 4, 6, 8, 10, and then 12. And then this is going to be in 1 second, 2 second, 3 second intervals. Or increments there. Okay, and so this is going to be, this scale is going to be in time, and this is going to be in distance at some time. Everybody follow that? Okay, so I have 2 ways of disturbing this mass that I have hanging from the ceiling. I can either push up on it, and then it starts bobbing up and down, or I can pull down on it and it starts bobbing. So, what does it look like I did? Right now it's in equilibrium at time equals 0. And the distance from the ceiling is getting bigger. So what did we do? We pulled it down first. Okay, so that's good to know. If this graph was upside down, That would mean I disturbed it by pushing it up first, okay? So we're going to answer some questions here. So the midline tells us what, just physically? Yes,
Like where to be on
at equilibrium, the equilibrium point. Oh. And when it's not moving, right? And it's in its natural state. The period tells us,
How long it takes for it
It's not a conflict.
right, how long it takes to, and I'm going to use,
for the spring to go back.
right, I'm going to use what I call dummy English. The time, how long it takes to go through an up-down cycle? Does that make sense?
Yeah.
Everybody
Did
under?
we just say cycle?
Yes. Through a cycle. Now, can I spell cycle? Goodness gracious sakes alive. Yes, I did go to college. But I did major in spelling. Clearly, you have to have fun with that, right? At least I'm catching myself. I'm embarrassed, but there we go. There it is. I did it. Yay. Okay. Congratulations, Mrs. Muller. Okay. So let's go back to what the midline says. The midline says, or it's equilibrium and it's not moving. In this case, equilibrium is what? D equals 10. The period tells us how long it takes to go through an up-down cycle. Mercifully, I was able to spell it. Okay, up-down cycle, and that's going to be, well, the period here. What is the time it takes to go? Yes, it's 1, isn't it? It's 1 second here. Everybody follow? Because I disturbed it by pulling it down, and then the distance got bigger, and then it's getting smaller, and it's going to go back. Okay, amplitude tells us
How high and low?
How stretched the spring?
how the maximum distance from the midline, right? Or from equilibrium. Do we say that? Maximum distance and the amplitude here is 2. Good. And it's going to be centimeters, right? Because that's what we're measuring in. The min and the max values tell us close. Yes. The closest it is to the ceiling, right? So the closest distance to the ceiling and furthest distance. From the ceiling. Good. All right, so now it says determine a sine function that would model the motion of the weight. Okay, so we're going to say it's d of t equals, now we know the amplitude, now we're going to name a sine or a cosine. I'd like to name one that doesn't have any phase shifts, so so sine can be a positive 1, and it'll be 2 sine, and I'm going to leave a space for b because we have to calculate that, right? And this would be t minus 0 plus 10. Good, because the midline or the equilibrium point is 10. So So how do we calculate what b is? We know the period is 1. So we say 2 pi over b is equal to 1. So this would be b equals 2 pi. So we put it right there. 2 pi goes right in there. Okay, and then I could ask you questions like, when is the weight 11 centimeters from the right? And you would set y equal to 11, and you'd see where they intersect. Yes. Here, go. Okay. Moving right along. This one is for homework. So what did we do differently here, real quick? Instead of pulling down, we pushed up because the distance got smaller, right? I know it's backwards, right? I just want you to think about that, okay? And so I want you to answer these for homework. And then I like to do number 5 next, which is about a zombie rabbit population in honor of the Walking Dead. So we have a lot of walking.
Let's say, or number 5.
Oh, is it the last one?
Yeah, it's.
Okay, it's number 7 for you, number 5 for me. I'm sorry. Zombie rabbits. It makes it more interesting, doesn't it? Because The Walking Dead is filmed here in Atlanta. So we might have zombie rabbits walking around. Anyway, hopping around, I should say. All right, so a zombie rabbit population in a national park rises and falls each year. Sounds sinusoidal to me. It reaches a minimum of 5,000 rabbits in January. So we're going to start with time equals 0 at January. Is that all right? So I'm going to put 5,000 here for my zombie rabbit population. And it reaches a minimum. By July, the weather warms up and the food grows more abundant. What do zombie rabbits eat? But zombie mice. Or something else. I don't know. Something smaller. Zombie what? Carrots? There we go. The population triples in size. So if it triples in size, it goes from 5,000 to 15,000. There it is. And then the following January, they die off again, and we have 5,000, and then 15,000. It repeats itself, and then 5,000. Okay? So the first thing we got to do is draw a really quick chart here. Graph detailing the zombie rabbit population. So I need the midline. I don't have it here. How do we find the midline? You average 15,000 and 5,000. So we add them together and divide by 2, which is 10,000. So I'm just going to put here 10,000. And there's my midline. And now I'm going to plot my data. We have 15,000 as my high spot and my 5,000, which is my low spot. And I understand that this is not to scale, but this is just to help me get my line curve named or give it an equation. So at time equals 0, we're starting at 5,000. I'm going to go from 0 here to 24. And half is 12. And halvesies again is 6, and then 18. All right. And then at the 6-month mark, we're at 15,000, and we go back to 5,000, and then so is this data giving me the midline number? The answer is no. But the zombie rabbit population is looking pretty sinusoidal in nature. Okay, so we need to know what the period is here. Heard it. It's 12. The amplitude. Good, 5,000. The midline, 10,000. And the increment, is it 6?
3.
It's 3 because it's the period. Remember, the increment is the period divided by 4, which is 12 over 4, which is 3. Okay, good. Now we're going to name a possible cosine function describing the zombie rabbit population. So we're going to call this zombie rabbits of T. We should make this a ZR up here, right, just to be fun. Now we have a choice. We can name a positive cosine or we can name a negative cosine.
Negative.
Okay, well or we can do both.
Yeah, let's do both.
Well, let's do both. Okay, it's a good practice. All right, so we'll name the negative one first.
Sure.
Negative.
5,000 cosine. Do I know B yet? I'm going to leave a spot for B. And then we're going to say T minus 0 plus 10,000. Now, why did I put 0? Because that's where I am starting if I'm in a low spot, yes? Okay, so how do I find out what this B is? You go 2 pi over B equals 12. Cross multiplying, we get 12B equals 2 pi. B equals pi over 6. Everybody concur? That's pi over 6. All right, let's name another name for our zombie rabbits. Let's make it a positive cosine. That's going to be 5,000 cosine of pi over 6 times T minus 6 plus 10,000. Good. Okay. Using your model, determine the population in September of every year. Now, what's tricky about these problems is January is not 1. January is 0. So what I do sometimes to help myself is go January, February, March, April, May, June, July, August, September, right? That's what I need. So I would go 0, 1, 2, 3, 4, 5, 6, 7, 8. So do I need it when time is 8, not 9, which is what we're used to September being. Okay, so watch that. All right, using our model. So we want ZR of 9. And I'm just going to use this first one. Is that right? I mean the second one that I can see better. The positive one. This is 5,000 cosine of pi over 6 times 9 minus 6.
It's 8.
It's 8. I'm using 8 instead of a 9 instead of 8. I just fell into my own trap, didn't I? Nothing like dirty laundry on video, but there we go. There it is. You're right. But I'm modeling humanity, right? Which is a good thing because we're all human. So I have to get over it. I know. I'm sorry. I'm embarrassed, but life is short. Okay, 5,000 cosine of pi over 6 times, well, what is this? This is 2 plus 10,000. Now I'm doing this by hand, but we could do it on a calculator. But I'm doing this because sometimes you don't need a calculator. This is the cosine of pi over 3, which I'm hoping you had a good enough pre-cal teacher. Ha ha ha. What is the cosine of pi over 3? 1 over 2. Good. So this would be 5,000 times 1/2 plus 10,000. And so that's, well, 500? Yes, because this is 2,500 plus 10,000. Did I do that accurately? It's 12,500 zombie rabbits. What? It's a lot. Yes, it is a lot. Okay, so that's all I have for this, and then the rest of the packet is your homework. And then there are a couple of problems in the book to do. All right. So thank you for your Kind attention.
Is this your next class?